I have a question related to the Euclid forte class.
Sure.
So I'm doing the wall bracket. I'm doing different methods of how it's used. So that's okay?
Yep.
And then I have three scenarios. So it's one where it's connected to the wall as a shell. Another where it's a ceiling getting pulled from a snap hook.
Great.
And I want to do a third scenario when it's the same from that second, but with different material properties.
Perfect.
Can you do that?
Yeah, sounds good.
And you said two loading and constraints. You mean like you have to move two altogether or two and two?
It's two different configurations. So that's exactly what you have. And so you have one situation where it's, it's like a shelf, and another one where it's a hook thing. And so that's all I mean by that. So
okay.
It doesn't refer to the number of constraints or number of loads that you have, but just the amount of different configurations, which you have two already. And so that's
all right. And then for discussion, I just want to have like how it's used, like depending on material property, is it better to go with the cheaper? Is it safe enough? Just right about that.
Perfect. Yep.
So, and I'm also following the format of the layout you have.
Yep.
But I'm also adding like three subheadings, which is like
one,
2, 3.
Perfect.
Cool.
Yeah.
All right.
As long as it's organized, that's the thing I care about the most.
Yeah, I was stuck on page. I was like 6 or 7 pages done, but I don't want to go any further, so I clarified that.
Okay. Yeah, no, that all sounds good. Oh, my trip was good. Yeah, it was a beautiful wedding, and so I was just really happy for my friends, and glad I could be there to be a part of it. So it was a little bit shaky on the way back, so I get motion sick really easily, and there was a lot of turbulence on the flight back from Ohio back to LA. So I'm actually still feeling some of the lingering effects right now. So I'm a little bit dizzy, a little bit nauseous right now. So if if that affects me today, then just bear with me. But it was a great trip overall. Happy I was able to go, but also happy to be back in LA. All right, it's 4 o'clock, so let's go and get started. Good afternoon, everyone. How's everyone doing today? Yes. Yes, it's that time, huh? But glad you guys could be here. I know it's really rainy outside, but hopefully everyone's staying warm and staying healthy. Okay. All right, so the plan for today is we're going to finish up our lecture notes on spinal biomechanics, and so we kind of got halfway through last time. And so today I anticipate us basically finishing up. Okay? If we have a little bit more time at the end, we'll go ahead and start our next topic, which is going to be on dynamics. Okay, and so this is kind of our last, our last topic in static biomechanical analysis. And so from here on out, we'll be working in a lot more motion into our analysis. Okay. All right, and so in terms of announcements, homework 5 has been posted, and so it's very similar in structure to homework 4, and so you're going to do some short answer questions. You're going to do some static analysis of the lower extremity and the spine. And I have another research question for you on homework 5 as well. Okay. And so I realized that the research questions, they take a fair bit of time for you to do. And so I know that, not only just in writing it, but also performing all the research and finding all the sources. So, it is a lot of work. And so, I just want to say that I appreciate your guys' works on that. Just because, I know I can ask a lot sometimes, but, you guys are the ones that are actually doing it. So, thank you for doing that. But the reason I'm giving you so many of these is that, those are kind of miniature versions of what the final project is going to be like. So the final project, you can think of it as almost like a bigger version of the of all those little mini research assignments, except, the final project is going to be much bigger than that. And so, kind of like what we talked about last week, the final project in this class, I'm having you do, you can work in pairs, or you can work even up to groups of 3. I'm fine with that. And you're going to be researching a kind of a specialized topic in biomechanics. Okay. So I'm going to let you choose. And so I started writing the specification today, although I still need to work on it quite a bit. And so hopefully by Wednesday, I'll have that ready for you. And then we can start to talk about, what to expect for the final project. You can go ahead and pick groups, and you can go pick the topics that you want to do as well. Okay. All right. And so I think that's it for the announcements. We do have another midterm exam but it's not going to be for another few weeks. I think it's going to be in 2 or 3 weeks. And so, we'll talk about that more as we get to it. But one thing I do want to make sure I get to you guys before this week is over is the specifications for the final project. Just because we are in week 10, and I always like to give, at least a month for you guys to work on the final project. Okay. All right. And so with that, are there any questions I can answer before we get started? Yes, next week. Yeah, correct. Okay, all right, so there's no questions. Let's go ahead and pick up where we left off. And so last week we left off talking about static analysis of the spine. All right. And so, I call this static analysis of the spine, but really, what we're focusing mostly on is the lower back or the lumbar spine. Okay, because as we'll talk about later when we talk about injuries of the spine, that's the part that generally people hurt most. Okay. Ooh. And so last week we did kind of a long example of comparing 2 situations, right? And so we looked at a situation where someone's performing a lifting task, and so they're lifting a heavy object off the ground, and we saw the kind of difference it makes for you to use proper technique and proper proper posture when you're performing this. Okay? Okay. And so we basically looked at the following 2 situations, right? And so, let's say that we have a heavy box here on the ground. And so we have this has a weight W, okay? And so we looked at a situation where the guy tries to pick it up, trying to bend over. And so he basically keeps his legs straight and he tries to bend over to pick it up, okay? And what we saw for this is that, this places a lot of stress and a lot of force on the lower back, okay? Because in order to kind of balance out this kind of large moment that's being created by the body, the spinal erector muscles or your back extensors have to exert a very large force. Okay. Okay. And so we compared the situation to, the same task, but instead of bending over to pick it up, what he's doing instead is he's, bending down with his knees, okay? Right. And even with this configuration, it causes a fairly large stress on the lower back, but it is significantly reduced compared to the other configuration, okay? Because whenever you're basically, whenever you're talking about any kind of stress on your lower back, you're mainly looking at kind of two main things, right? And they're very closely related. Okay. First thing you worry about is the magnitude of the force that the spinal erectors have to exert. Okay. Okay. And so those muscles are among the hardest working muscles in your body, just because of the amount of force that they have to exert on a consistent basis. Okay. And the interesting thing about those muscles that we talked about last week is that a lot of times you don't really realize how often that they're actually that they're actually in tension, because a lot of times just by passively standing or passively sitting down, your spinal erector muscles have to actually exert tension in order to maintain balance, right? And so me just standing here right now, my spinal erectors are actually contracting just so that I don't kind of topple over forward like that. Okay. But a lot of times we just don't think about it because they're just kind of always in tension. It's the same thing with your heart, right? And so the heart is another muscle that that is constantly pumping blood, but you just don't realize it because it's kind of always there. Okay. The difference is that you have much better control of your back muscles than you do your heart. Okay. And so going along with point one right here, the harder that your spinal erector muscles have to work, or the more force they have to exert, it's going to place a lot more stress on your vertebrae, on your spinal column. Okay. Okay.
Is the spinal erector muscle like an involuntary muscle, or we just done it for so long that it's got used to doing it?
Yeah, it's a voluntary muscle, but it's just almost always acting that you just don't really think about it. Yeah. Mm-hmm. Right. And point number two right here, this is the one that really leads to injury because we'll be talking more about injuries, but we talked about things like you can have a hernia, right? A herniated disc. Or you could have a fracture in your vertebrae, right? And so the more stress that you're placing on these bones, the more risk you are of injury. Okay. And so the whole idea with all of these things like proper technique, proper posture, is to lower one. Okay. Okay. And so we want to minimize number one as much as possible, because the more we minimize the amount of work our back muscles have to do, the less likely or the less risk we have at getting injured. Okay. All right, question. So more muscle force needed to lift something means more stress on the spinal column. So if a person has a lot more muscles, then the stress on the spinal column, would that be lessened? And so you're asking if so you're asking if someone has a very muscular back, then it would put more or less stress on the spinal column. Generally those two are connected. And so, for people that kind of work out their back a lot, it kind of naturally strengthens a lot of the softer tissue around that area as well. So like it also strengthens the tendons. It also strengthens the ligaments in that area. And so, generally speaking, building up muscles in your core is always going to be a good thing for you, okay? Because just by naturally strengthening your back, you're also strengthening the other parts of your core, like your abdominals and your obliques, right? And so by doing that, you can also use those other kind of antagonist muscles to kind of relieve some of the tension from your spine as well. Yeah. And so,
How much force you add is still about the same amount of stress on this. So let's say it's stronger, but they'll still experience more stress as you're applying more muscle force to it.
yeah, so you'll be applying more muscle force, but then you'll have more antagonist muscles as well on the other side. And so those will kind of, take off some of the strain as well. Yeah. Yeah. So generally, as you get more fit and more muscular, that's what kind of tends to happen, is that your antagonist muscles build up and then less of the load gets placed on your spine. Yeah. Generally, the more load you can offload from your bones, the better it's going to be for your long-term health, because your muscles are a lot easier to heal than your bones are. Mhm. All right, and so that was the analysis we did last time, and so that was with respect to kind of a, I would consider a fairly strenuous task. Lifting up a heavy load from the ground is not an easy thing to do. But what we'll look at today is kind of a similar analysis, but from a different kind of viewpoint, where we're instead going to be looking at your posture when you're just performing like an everyday task. Okay. And this is going to lead into a discussion of ergonomics or human-centered design. Okay, because even something that you wouldn't really consider strenuous, something that's just your everyday life, even that can place a lot of stress on your back if you're not careful. Okay. All right. Any questions on this? Okay. All right. And so let's look at the kind of a similar situation, but in the workplace. Okay. All right. And before I kind of get started, I'm going to go ahead and put a plug in for one of my good friends' classes. And so Dr. Lee actually teaches a class on human-centered design. So I believe it's EGME 480. Okay. And so that class is a very, very close cousin to this class. And so if you get the chance to take that class, I would highly recommend it. It's really interesting. Or you might be in it right now, which is great. You're kind of getting kind of both perspectives at the same time. Okay. Okay. And so the whole point of that class is, how do we design workplaces, or how do we design, machines for people to use that work well for them. Okay, and biomechanics actually plays a really big role in that, because a lot of the idea of designing an effective workplace is to design one that that places as minimal stress on the human body as possible. Okay, and so another way you can think of that class is ergonomics. Okay. And so a very, very close cousin to this class. Okay, and so let's consider three kind of similar cases for this. Okay. And so in each case, we have a person that's going to be bending over more and more for him to do his work. Okay. And so let's say that we have a person like this. And so let's say this is case one. Okay. And so in case one, let's say that he's working on something on a table in front of him. Okay. But the person's able to stand up straight during this task. Okay. Okay. And in fact, or actually, let me draw the three cases, and then we'll put numbers. Okay. Case number two. And so in case two, we have basically the same situation where a person is working on on a table in front of him. But let's say that the table is designed so that the person has to bend down just a little bit in order for him to perform his work. Okay. And so this person kind of has to kind of slouch over just to kind of perform that. Okay. Something that we don't really think about a lot, but we'll see that it makes a big difference. Okay. All right. And then case three will be kind of the more extreme case, where case three will be this person will have to bend down a lot in order to perform this work. right? And the way we're going to characterize these is by the by the angle at which the back has to bend over. Okay? And so each of these different cases will have a different angle theta through which the body has to bend over to perform the work. Okay. All right. And so I like this example because it's something that we often don't think about. And so if you work kind of a job like this where you have to bend over, it's not something that people usually will complain about all that much, right? Especially if you're kind of new to a job and you come to this job and if the first thing you say, oh, I have to bend down too much to do my work, I think a lot of people don't feel comfortable about doing that because it's it kind of sets a bad, they think it sets a bad impression for their for their new workplace. Okay. And so one thing that always comes to mind is I have an uncle who works in who's a chef, and he always he always talks about how important it is for him to work on a surface where he feels comfortable with a good posture. Okay. And we'll see through this analysis how important that is and how much more strain you put yourself into, even without really lifting something heavy. And so here, we're going to assume that the person's not even going to be interacting with the thing on the table. And so in these cases, you're basically only going to be supporting the weight of your head and your upper body. Okay. And so even in these cases, we'll see that posture makes a really big difference in how you perform your work and how much strain that's going to put on your back. Okay. And so generally speaking, just to kind of give you a hint of where we're going with this analysis, generally you want to design your workspace to limit the amount of bending over that you have to do. Okay. All right, question, let's see. All right, it starts to feel uncomfortable after the first 2 hours. Yep. Yes, yeah, definitely. You definitely don't feel it at first, but then after you work on it for a while, then it definitely gets to be uncomfortable. Yeah, it's at these times usually I'm a pretty short guy, and so usually I don't envy or I envy taller people a lot, just because at least when I was younger, being tall meant that you were picked first in basketball, and then you could you lined up first when we lined up in height order and things like that. But with regards to how much more stress that puts on your back, I can say I don't envy tall people at all anymore. It's a lot easier for me to work and not put strain on my back. Yeah. All right. Any questions on this before we start working on the numbers? Okay. All right. And so let's start with the free body diagram to show to kind of show all the weights in action. Okay. All right. And so let's do just a simple kind of 2D analysis. And so let's assume that the entire torso is a stick. Okay. Right. And so at the bottom of the stick right here, we have the spinal joint. Okay, so that's going to be kind of the focus of our analysis. Right. And let's say that we have 2 weights that are being applied here. Okay. All right. So let's assume that we have one weight here, W1, and this is going to be the weight of the arm, shoulder, and head. Okay. Okay. And then we have another weight, W2, which will denote right here. Whoa, that's weird. Motion. There. Thanks, Jacob. All right, W2. So W2 here represents the weight of the trunk. Okay. And so that's basically the weight of your kind of your abdominals and everything. Okay. All right, so those are the two main weights that we're supporting. Okay. And the muscle that's performing the support is of course going to be your back muscles, okay, your back extensions. And so we'll assume that it acts right here. Okay, so that'll be our FM, that's our muscular force. And we'll assume that it acts with an attachment angle of alpha. Okay, and that angle alpha is measured relative to the spine. Okay, so pretty classical definition for a muscle attachment angle. Okay, and then our main variable of variation here is going to be this angle theta right here. Okay, and so that angle is going to describe how much we're slumping over. Okay. Okay. All right. And so let me go ahead and put the joint reaction forces here. Okay. And so this is going to be a unique problem where I'm going to describe the joint reactions in terms of down the length of the spine and perpendicular to it. Okay. And you'll see why later. Okay. And so typically I don't do this. And so, if you look at the homework problems, most of the times I do the reaction forces in terms of the X direction and the Y direction. But for this particular problem, I'm doing it, down the length and perpendicular to the length of the column. Okay. All right. So let me go ahead and label all these points. And so the spinal joint, I'll be labeling with point A. And then going up the spine, I'm labeling all the other points with other letters. Okay. All right. And so the reason I'm labeling these points is so that we can give some distances here. Okay. So the distance between A and B is going to be 0.15 H. Okay. The distance between A and C, this is going to be 0.2 H. And the distance between A and D, or the entire length of the spinal column, will be 0.3 H. Okay, where H here is the height of the person. Okay, and so these measurements here are based on anthropomorphic data, and so this is kind of the average length of a person's spine. Okay. And so if you want to do this analysis with your own height or the height of someone you can just plug their values in for H. Okay. All right. And so I think that's everything. Okay. All right. And so just like we usually do in these problems, we have three unknowns. And so we're going to input our three equations for static equilibrium, and we're going to solve for the muscle force and the joint reaction forces. Okay. And we're going to do this for three different angles of theta, okay, which correspond to our three different cases. So let me go ahead and find out what those angles are, okay. And so for case one, let me go ahead and make a table right here, okay. And so for case one, the angle theta is going to be 85 degrees, and so we're basically going to be standing almost straight up, okay. For case two, our theta is going to be 75 degrees. Okay, so it's bent over just a little bit more, although not too much. Okay. In case three, where the person is bending over a lot, we'll assume that the angle is 60 degrees. Okay. All right, and so we're going to compute the muscle force and the joint reaction forces. Oh, and we need alpha too. Where's alpha? I believe alpha here is 13 degrees. Yes. All right. Any questions on this before we jump into solving?
Alpha will remain the same as the case.
Wait a second.
Alpha will remain the same angle depending on
Yes.
the-
Yeah. So alpha will be the same for all three cases. Yeah. Mhm. Okay. All right, so let's go ahead and start solving this. All right, so first thing we're going to do is we're going to sum up the forces around the joint, just as we normally do for these problems, okay? Or sum the moments, I'm sorry, okay? And so remember, the reason we do this is that this eliminates both of the joint reaction forces from the equation, okay? And so if we do this, we have three contributions to the moments, okay? So we have the two from the weights, okay? And so let's do the contribution from W2 first. And so W2, we're going to multiply this by the moment arm for W2. And so this can be 0.15 times H times cosine of theta. Okay. And so that's the horizontal distance between W2 and the joint. Okay. Next, we have the moment contribution from W1. And so we have a minus W1 times 0.3 H cosine of theta, okay? And then we have plus the contribution from the muscle force, okay? So it's going to be plus Fm times sine alpha, right? Because we have to get the component of the force that's perpendicular to the spine, okay? And we're going to multiply this by the moment arm, which is 0.2 H. Okay. And all of this is equal to 0. Okay. All right.
W1, W2 perpendicular to the-
They're vertical up and down. And so the reason we use cosine is because we want to get, like, say, the horizontal distance from here to here. And so we use the length from A to B from here, and then we multiply by cosine of theta to get that. Yeah. All right. And so this equation only has one unknown. And so we only have Fm, which is an unknown here. And so we can go ahead and cross out all these H's because they're a common multiple across all of these things. Okay. And so if we solve this equation for Fm, what we get is Fm is equal to cosine theta. Okay. I'm just going to go ahead and factor that out of the numerator. Okay. And so this can be 0.15 times W2 plus 0.3 W1, all divided by 0.2 sine alpha. Okay.
Well, in this case, we're assuming that Fm is horizontal.
The FM.
Yeah.
So the FM is not quite horizontal. This figure makes it look like it is, but since the alpha here is only 13 degrees, it's actually pointing more down like that. Yeah. And so because the alpha is constant, you know, the direction for FM is going to change in each of the configurations. Mhm. All right, and so we can go ahead and plug in values for W1 and W2 as well. Okay. And so typical values for W1, W2 based on anthropomorphic data, as you can say that W1 here is equal to 0.18 W, okay, and W2 is equal to 0.36 W, okay, where W here is the weight of the whole body. Okay. And so of your entire body weight, what this is saying is that you're, for W1, remember W1 here represents the weight of the arms, shoulders, and the head. And so what this is saying is that your arm, shoulder, and your head take up about 18% of your entire body weight, whereas your trunk takes up about 36% of the body weight. Okay, and so that's kind of what we're saying with this these numbers here. Okay, and then with all of those things fixed, you can see that the main thing that's going to change this value is going to be the value for theta. Okay, and so we can go ahead and plug in each of the values of theta that we had on the previous page. All right, questions. So for the FM, we use sine alpha because it looks horizontal. If it was more vertical force, we would use cosine. So remember, this is in this case, we're summing up the moments, right? And so we're summing up the moments around this joint right here. And so whenever we're summing up moments around a joint, we want to get the component of the force that's perpendicular to the line of action. Okay. And so here we have this line here that connects the joint with the force. Okay. And so we want to get, and so when we're summing moments, we want to get the component that's perpendicular to this line, right? And so in other words, we want the component of F in this direction. Because that's going to be the one that actually produces a rotation or a torque around the joint. Okay? And the way we get that component is Fm sine alpha. Because if we did Fm cosine alpha, that would be along this line of action, and so that wouldn't produce a torque. Yeah. Yeah. So for these torque equations, you kind of have to have a little bit of a different mindset than the force equations, because you have to think about what component is actually going to produce rotation. Yeah. Yeah. All right. And so that's the moment equation. And we'll list out what the values for this are depending on the value of theta. But before we do that, let me go ahead and write out the expressions for the reaction forces. Okay. All right, so first let's do the reaction force along the spinal column. Okay. And so if we sum up all the forces in the A direction, okay. A here standing for axial, what we get is JA minus W2 sine theta minus W1 sine theta minus Fm cosine alpha, okay, and this is equal to 0. And so if we plug in for all of our variables here, assuming that we have the expression above for Fm, what we get is JA is equal to W1 plus W2 times sine theta plus Fm cosine alpha. Okay. And remember, this is in the direction of the spine itself, and so this is not in the x direction. It's not in the y direction. It's in the direction of the spine. Okay. And the reason I did this is so that we can strictly quantify how much compressive forces is being put on the spine. Okay. Because what we'll see is that because the muscle force has to kind of pull the upper body back, that's going to put a compressive force on your lumbar spine. And so what this force here is going to represent is what that compressive force is, and basically how much stress your lumbar spine is going to be put under. Yeah.
Could you give the force component for
Oh, yeah, yeah, for sure.
I'm just having trouble we're having trouble seeing how the sign is gonna put it along the spinal.
Yeah, yeah, yeah. Let's do that one. That one's a little bit tricky. Yeah. So the question is, how do we get sine theta right here? When we're summing up the forces in that direction. And so let me kind of draw a bigger line right here. And so let's say that this angle is theta, just like we defined it. Okay. And our W1 and W2, they're the same. And so let me go ahead and just draw a line like this. And so in this case, I guess this would be W1. All right. And so, in order to sum up the forces along the spine and, perpendicular to the spine, what we want to do is we want to break up this, this force right here into those two components. Okay. And so we can see that the spinal, the spine goes in a direction like this. Okay. And so, let's make a right triangle, where one of the edges of the triangle is parallel to the spine. Okay. And so that's what I've drawn here in this orange line. Okay. Okay. And then we're going to draw a component perpendicular to the spine. And so we're going to draw one like this. Okay. Where this is going to make a right angle here. Okay. All right. And so when you draw a triangle like this, you kind of have to draw where the angle is, which I think is kind of the hardest part. Okay. And so you can kind of almost think of this as, we're kind of, in this case, we're kind of almost flipping, or we're rotating the entire coordinate system by 90 degrees. Okay. And so in here, when we draw the angle like this, we can see that this angle here, theta, is an angle with respect to the horizontal. Where the main kind of the main hypotenuse, or the main kind of length that we're considering, is the actual spine itself. Okay. And then we're defining the angle with respect to that line with respect to the horizontal. Okay. Here, since we have a vertical force, we're kind of flipping it, vertically, right? And so where you would actually put this angle is actually right here. Okay. And so when you take, a vector here that's purely vertical, and you break it up into components, along with and perpendicular to an oblique line, then the angle that you put onto that kind of pseudo triangle is with respect to the vertical. Okay. And so this here is the same angle as down there. Okay, but we do this with respect to a vertical line. You can just leave it off unless you guys want to. Yeah. Okay. And so that's how I got that sine theta, because we're in the previous equation, I was summing up the forces in the direction parallel, right? And so to get this parallel component right here, considering this W1 is the hypotenuse of this triangle, is to do W1 sine theta. And this is going to be the component of W1 along the spine. Okay. I can't see the rotation of the angle for the vertical force W1. Yeah, it's hard. And honestly, like for a lot of times when I'm doing these problems, I kind of have to draw it myself. And, and actually kind of the way that I drew this kind of doesn't really do you any favors, because right now it's a little bit hard to tell because I drew this angle, visually, it almost looks like it's 45 degrees. Okay? And so that's kind of the most unhelpful thing that you can do. And I'll show you a trick that I usually do. If you're not kind of sure which way to kind of put the angle, is to kind of draw the angle that's more skewed to one side or the other one. Okay. And so I'm going to show you, and I should have done this first, and so I apologize. But if I draw this line kind of more straight up, then it'll be clear where you kind of put that angle relative to them. Okay. And so I'm going to do that on the next page. But is anyone still writing stuff down on this page here? Okay. All right. So what I usually do to kind of help me out with the trig here is to kind of bias the drawing kind of to one side or the other. And so that when you draw kind of these auxiliary lines like these ones, it's clear kind of where the angle has to go. Okay. And so if I draw another line that's kind of mostly vertical like this, it's a little bit too vertical. Okay. Maybe like that. Maybe a little bit more vertical. Maybe something like that. Okay. Gia, do you need you look at this one for a minute? Okay.
Professor, is this just a geometric property?
Yeah, it's just geometry. Okay. Yeah. It is hard though. I mean, I always have to do this, and so if you look at my notes, I have all these little triangles drawn in just because it's hard to kind of look at it at a glance, even when you're doing it for a while.
People confuse some of it with the one we're using the regular X and Y axis coordinate system. It's now tilted.
Yeah. Yeah, it's I know. Yeah, it's and I know that's good, but that's kind of why in the lecture I kind of give you both sides so that we kind of get practice with both.
Yeah, but at least this way we don't have to
Yeah. In the homeworks typically, and for the exams typically, I'll give you, I'll tell you just to do in classical X, classical Y, because I think that kind of makes most sense. And during the exam, you're kind of stressed for a lot of time, and so I don't want you to kind of have to do all this in the exam. But I did want to show you this because, particularly for this example, it makes a lot more sense to do it, along the spine and perpendicular to the spine, because, we're mostly concerned with what is the compressive force on the spine in this case. Yeah. Mm-hmm. All right. And so, okay. Just like before, we have a vertical force like this, okay? And then we're going to draw a component parallel to the spine, okay? And so parallel will be something like this, okay? And then perpendicular will be something like this. Okay. All right, and so just like in the previous figure, parallel is in the orange and perpendicular is in the purple, okay? And if we define this angle theta, right? Right, and so you can see from this triangle, we have kind of two options or two places where we can put the angles. We can either put it on this corner or we can put it on this corner, okay? But from the image right here, you can see that this angle right here is greater than 45 degrees, right? Just kind of visually, just kind of how we drew it, right? And so when we go to assign this angle on this triangle, we should go and apply it on the angle that looks like it's bigger than the other one, okay? Okay. And so if we compare, the upper corner and the lower corner, obviously the upper corner here is a bigger angle than the smaller one. And so that tells us that, we should apply the angle on that one, okay? And so, you can use these kind of visual tricks to kind of help you, choose, where to put angles and how to measure stuff, okay? And so even if you have to kind of modify kind of the tilt of the geometry, and so let's say that I gave you a figure, and it kind of looks like it's 45, you can go ahead and exaggerate that one way or the other, just to make sure that you're assigning your angles in the right places. Okay? And so I do this all the time, just to make sure I assign angles in the proper places. Yeah. Okay. All right. And so that's kind of how I got, W1, W2 sine theta, because what we want is this component along the spine. Right?
It was drawn the other way, so I was just really confused about how to do it like that.
Mhm.
Which is why I wanted to do it. The other triangle just makes no sense.
Mhm.
I was like, where's the hypotenuse? How is this gonna be a right triangle? That makes sense.
Yeah. So whenever you're going to break things into components, you always want to make sure that the vector that you're trying to break into components, that's going to be the hypotenuse of the right triangle. All right. And so that's the sum of the forces in the axial direction. Let's do the sum of the forces in the perpendicular direction. All right. And so here in this direction we have JS. It's an A, JS plus W1 cosine theta plus W2 cosine theta. Here we're using, the cosine component because we're doing perpendicular to it, plus FM sine alpha. And all of this is equal to 0. Yep.
I'm confused. Why is W2 positive?
I guess the reason is because we define the positive. Oh, you're right. Yeah, W1, W2 should be.
Or couldn't you, I guess since there's 3 JS and W1, W2, they will all be going the same way, right? So then couldn't you just make that negative?
Yes. Yeah, you're right. Yeah. So that is a typo. So the FM should be going the opposite direction. Thank you. Yeah, because all the W should be pointed this way, right? Whereas the FM component should be going the other way. And so this should definitely be a minus sign right here. For the JS, I think originally I have the JS pointed down, down in that direction. So I think yeah, putting the negative there kind of puts all the signs. Yeah, all the signs. All right, question: could I have lined up that the W along the joint and then rotate the blue line towards the red? Rotate the blue line towards the red. Let's talk offline about that. It's I'd have to kind of draw it out to kind of visualize it, but I did want to make sure I get through these notes today. But yeah, we can talk after the class. Okay. And so if we oh, I do have the minus here. I just kind of missed it. All right, and so if we solve for JS, we get JS is equal to minus W1 plus W2 cosine theta plus FM sine alpha. All right, and so now that we have equations for the joint reaction forces and the most force, we can go ahead and solve for their values for 3 different cases. Okay, and I'll go ahead and summarize those results into a table, just so that so it's kind of easy to see how they are for each case. Okay. All right, any other questions on this? All right, and so let's go ahead and plug in the different values of theta, and then we'll compute, FM, JA, and JS. So let me go ahead and summarize this in the table. So we have FM, we have JA, we have JS, and all these results here are going to be relative to the weight of the body. Okay. And so we have 3 different cases. And so I'm going to go ahead and write out the angles for each case. And so case 1, remember the angle is 85 degrees. Case 2, the angle is 75 degrees. And in case 3, the angle is 60 degrees. Okay. So let's scuff there. All right, so case 1 is the person standing up as straight as possible. So for this case, we expect the forces to be the lowest in here. Okay? And so if you plug in all the numbers, what you get for FM in this case is, we use green. Okay? What we get in this case is that FM is equal to 0.209 W. Okay? JA is 0.74 W. And JS here is about 0. So you plug in, and then you get about 0 for the shearing force. All right, so now let's do case 2. And so case 2, we've changed the angle to 75 degrees. And you'll see that even with just that very, very slight tilt, and so we're only tilting our body 10% more relative to case 1, you're already going to get a much bigger increase in all of these forces. Okay. And so for the muscle force, you're going to get about 3 times as much muscle force. And so you're going to get 0.62 W. Okay. For the joint reaction forces, it's going to be 1.13 W. Okay. And the shearing forces, again, are going to be about 0. Okay. All right. And if we do the calculations for theta is equal to 60 degrees, we'll see that the muscle force increases by another factor of 2 again. Okay. And the joint reaction force is going to increase as well. Okay, so it's going to be 1.64 W, and the shearing force again is going to be about 0. Okay? Not exactly 0, but very close. Okay? And so basically, what that's saying is that we're not putting any shearing loads on the joint. All of the loads that we're placing on the joint is purely compressive. Okay? All right. And so you can see here that, even without any loads, even here, we're just supporting the weight of the body, or not even the whole body, just the upper body, then, you're subjecting your back muscles and your lumbar spine to a lot of forces. Okay. And in particular, I want you to look at the difference between kind of the ideal case of 85 degrees and the most non-ideal case of 60 degrees. And so in between these two cases where, we're only increasing the tilt by about 25%, which actually is kind of significant, although when you say it in terms of numbers, it's not that much. Okay. And so when you change your tilt that much, you can see that your muscles have to work 6 times as hard, with that kind of slight tilt. Okay. And in terms of the force that you're putting on your joints, you're increasing that by a factor of about 2. A little bit more than 2x. Okay. And so that's pretty significant, for a case where we're not adding any loads at all. And so we're not, case number 3, we're not picking up anything. We're not holding anything in our hands. The only thing we're changing is just our posture. It makes a dramatic impact on how much force that your body has to exert. Okay. And so, if you can imagine that, especially if this is for your workplace, if you have to expose your spine and expose your back muscles to this much more force, for a long periods of time, for a lot of these jobs, you kind of have to stand at your workstation for hours, that's going to build up over a long period of time. And, that's going to add to, a lot of sore shoulders, a lot of sore backs, just because you're just working so much harder just to kind of bend over just a little bit more. Okay. And so making sure that your workstation is adequately designed for you so that, you have good posture and you're not putting any strain on your back is really important. In terms of the long-term health of your body. Okay. All right. Any questions on this? Yep.
Like bad posture and lower back
Sure.
forces.
Mm-hmm.
Like, so like, let's just say I sit like this, right?
Mhm.
So does bad posture put more pressure on your lower back because when you bend over like this, it increases the moment arm from here to here?
Yep. That's definitely a big part of it for sure. Yep. Mhm.
And then what about when it comes to like lifting too? You know how they say you should never round your back or whatever. Or, I mean, I don't know what the number, but you should try to like limit rounding your back when you're lifting any type of weight,
Mhm.
squatting or deadlifting. Is it because the moment arm becomes so much larger there and then you're just placing unnecessary force on your lower back?
Exactly.
Or is there like also
Nope.
increased chance of soft tissue injury, not just from the increase in the moment, but also from other factors?
Yeah, it's definitely all related. And so kind of the worse posture that you have, you're putting more unnecessary strain on kind of the soft parts of your bones. And so with respect to lifting weights, it's especially important because if you have bad posture, then you're kind of doing two things. And so you're putting yourself at unnecessary risk for injury, and you're also not working out the muscles that you want to be working out at the same time too. And so you're doing so much extra work, but none of that extra work is actually going towards something productive. It's just going towards hurting yourself, basically. And so having proper lifting technique is important so that you get the most out of your workout and you don't hurt yourself at the same time. Yep. Mm-hmm. Yep. All right. Any final questions on this?
You said at the angle map determines how much shear force.
You said shear force?
Yeah, shear, yeah, shear force.
Yeah. So for the shear force, and kind of the reason I included that here is that you're actually not going to get that much shear force contribution just by kind of doing your posture. Usually, you kind of need some kind of external force to kind of apply some shear. And so we'll talk about that actually. And so one common situation where you apply shear force on your spine is through whiplash. And so if you kind of if you've ever been in a car accident, you know that your head kind of whips like this. And so that sudden whipping motion, that places kind of a lot of shear on your back. But just from your posture and just from kind of lifting something, that's mostly going to be compressive. It's not going to be that much shear. Yeah. So it usually has to be some kind of external thing that shear. Yeah.
What about when it comes to deadlift? I can understand when, or like just any lifting off the floor in general.
Mhm.
Like I could understand when you get to the top position, how that would put a lot of compressive force on your joints. But like, what about when you're in the starting position? Because like there's some deadlifters that they do sumo deadlift or whatever, they can get like really strict. But for a lot of conventional deadlifters, like you start like this, like in that bottom position, wouldn't you be putting a lot of shear on your lower back?
Oh yeah.
In that case, or even like picking up a box off.
Yeah. So for kind of the heavier external weights that you're applying, that's going to put more shear on your back as well. So that's definitely a case. Anytime you have to kind of, because it's all kind of, you're trying to maintain static equilibrium. So whenever your spine's kind of angled like this, and you're applying kind of a weight kind of almost, or at least there's a significant component perpendicular to that, then you're going to have some shear. Here, even in the worst case, the angle was never too extreme. So 60 degrees, it looks like a big kind of slouch, but it's not as much as you probably would for like a deadlift. And the weights here are pretty small because we're just supporting the weight of our upper body, basically. Yeah. All right. And so I did have one more example that I wanted to cover, although I wanted to make sure I cover injuries before we go. Because on Wednesday, I really want to start about motion. And so the last example that I had on the notes is with regards to your neck, actually. And so we've been spending all our time talking about the spine, but you have some neck extensor muscles in your neck that almost always have to be active too, just because your head, if you look at kind of the side profile of your head, your head's kind of more front loaded. And so if you kind of just don't think about it, your head kind of naturally just wants to droop. Just because the center of mass of your head is kind of more forward compared to the joint in your neck. And so your neck muscles are another muscle that always kind of has to pull your head back, just kind of make sure that your face is upright and you're not doing like this all the time. And so, I have just a very quick example of that in the notes, but it's not any new math. And so I'm going to go ahead and skip it in the lecture. But you can go ahead and take a look at it in the notes, because I did want to make sure we talk about injuries today before we close up our section on static analysis. All right, so let me go ahead and switch to my computer screen here. Okay. And so this is kind of the end of the lecture slides that we started last Wednesday. Okay, so let's talk about some common injuries of the spine. Okay, and so probably the most common injury of the spine that people experience is just simply lower back pain. Okay, and so lower back pain is so common that about 85% of people will experience it at some point in their lives. And honestly, I feel like that number is actually a lot higher because if you're talking about people experiencing lower back pain at some point in their lives, that has to be basically almost everybody. Okay. And in terms of the economics, this is probably the most frequent and also the most expensive workers' comp claims in the US. Okay. And so people just all the time just kind of injure their back in their throughout their work. And you can file for workers' compensation and your company has to compensate for you. So, and so it is one of the most often injured. Okay. In terms of the causes, mechanical stress, of course, is one of the most major causes. Okay. And the rate of incidence is much higher in occupations that require handling heavy materials. Okay. And so just like the example that we talked about last week, right? And so if you're lifting, lots of heavy materials from the ground and you're doing this repeatedly, that's going to place a lot of strain on your back. And of course, you're going to injure your back a lot more for, in those situations. Okay? But it's becoming, as kind of more of the workforce kind of turns to more kind of computer-oriented jobs or, sitting-oriented jobs, it's becoming more common for those as well. Because, generally, I think, people aren't really designed to be sitting down for, for hours and hours along during the day. And so I think kind of the natural tendency is to kind of slouch in your seat to kind of lean back, right? And so that places a lot of stress on your lower back as well, okay? And so it's becoming more and more common for those people, okay? And so, there's not just one way to injure your back. And so it can result from either carrying one large load and kind of just throwing out your back like that, or it can be the repetition of a lot of numerous small loads, or the accumulation of a lot of bad habits that you have in the workplace. Okay. And so even though we've studied lower back pain a lot, there's still a lot of cases where in here I say that they have unknown origin, but I think what that really means is that it's hard to pinpoint one exact cause because really it's kind of an accumulation of a lot of things. Okay? And so I think this is going to be relevant for a lot of you guys because you're going to graduate from here and you might get a job where you kind of sit at a desk for a long period of time. Okay, one simple device that you can get is a kind of a lower back cushion, and so you'll probably see cushions that are called lumbar support, things like that. It's basically just a pillow that kind of sits on your lower back, kind of right above your butt, when you're sitting. And that thing actually, it seems like it doesn't do that much. And I have to admit that, when I first saw it, I thought it was kind of a waste of money. But, if you compare your posture and I kind of regret not assigning this as a homework problem. If you compare your posture, when you're kind of sitting without that lumbar support and you're kind of slouched over like this versus, you're sitting with that lumbar support, it kind of forces your lower back into a curvature that's much more healthy and places a lot less strain on your lower back. And so, if you're in a position where you have to sit a lot, think about investing in one of those. And it's going to be life-changing. And a lot of times, you can get your company to pay for that as well. Because you might think that your company might not want to pay for you for a cushion for your chair. But what they definitely don't want to pay is a costly lawsuit when you sue them for workers' compensation. And so,
I was going to say, or just workers' comp insurance, they probably have to pay.
Exactly, right. And so most workplaces actually, the whole idea of human-centered design and ergonomics is kind of companies are seeing that it's a very cost-effective way to cut down on workers' comp. And so if you ask them for something like that, something simple they can buy on Amazon for like $10, $20, then they'll happily do it for you. And if it makes you more comfortable, gives you less back pain, I'd say that's a win for everybody.
That's the other question.
Yeah.
So I'm saying this, I know, like the lumbar support that puts like this.
Yeah.
I'm seeing now a lot of like gaming chairs and stuff like that, and just general like expensive office chairs. They also have like a neck pad.
Yeah.
So like just putting your neck in a similar position like that, or I guess more straight, also have the same benefits for the vertebrae in your neck.
Oh yeah. Oh, yeah. So the question is, a lot of furniture nowadays, especially like gaming chairs, also have like a support for your neck. And it's a similar logic where like your lower back kind of has a natural curvature that it wants to maintain to minimize stress, and for your neck as well. And I think for gamers especially, they kind of lean their heads forward kind of a lot. And the more they kind of lean forward, the harder your neck muscles have to work. And so by kind of forcing your neck to be at a certain curvature, it helps to minimize the stress in your upper spine for sure. Yeah. That has to do more with your shoulders and kind of your neck. Yeah. All right. Any questions on this? Okay. All right, fractures. And so fractures, I would say, are less common for your spine, but they can happen. And the way that they mostly happen are through some kind of traumatic event. Okay. And so you have some kind of traumatic blow to your head, to your neck, or even to your spine. So these are the kinds of events that can cause a fracture. Okay. And so the most common cause for fracture of your spine happens in the cervical spine. So kind of up near your neck. Okay. And that typically happens when you sustain kind of a large, blow kind of on top of your head. Okay. And that places kind of a large, compressive stress on your neck kind of all at once. Okay. And so acute fractures can also happen when you're carrying a large load. Okay. And so if you're doing like a big event or big task like weightlifting, or you're lifting a heavy object, and you kind of do it a little bit too quickly where, your muscles or the ligaments and the tendons can't sustain that load, then, all that load is going to be placed on your vertebrae, on your spine bones. And so that can also cause some fractures as well. Okay. And any kind of fracture to your spine can be catastrophic, because remember, one of the main goals or the main responsibilities for your spine is to protect the spinal cord. And so if you injure the spinal cord, that goes to your whole body. And so any significant injury, almost certainly will cause paralysis, or even in extreme cases, it can cause death as well. Okay, because if your brain can't communicate to all the vital organs in your body, then that's that can be fatal. Okay. And so stress fractures are also common. And so remember, stress fractures are basically fatigue fractures. And so, those are fractures that take place, as you kind of load and unload it over, various periods. Okay. And this is especially true when the lumbar spine is hyperextended. Okay. And this is dangerous because, spinal fractures, they tend to not really heal on their own, or are very slow, since the spine is so naturally loaded often in normal activities. And so it's kind of hard for the body to kind of get blood vessels through that part of the spine. All right. Any questions on this? Okay. All right. So let's talk about disc herniation. And so we talked about this a little bit at the beginning last time when we talked about what these discs are, but now we can talk about the injuries more in general. Okay. So remember, in between each of your vertebrae bone, you have these kind of soft cartilage discs called, discs. And if you place kind of continuous large loads on these discs, then they can start to bulge out. Okay. And so whenever these discs start to bulge out, we call this a hernia or disc herniation. Okay. And so they account for maybe about 1 to 5% of all back pain. Okay. But if it does happen, it can be extremely, extremely painful. Right. And the interesting thing is that the disc itself doesn't actually feel any pain because there's no nerves that run through this disc. But what actually causes pain is that when the disc bulges out, it actually starts to impinge, or it actually starts to to touch the spinal cord, right? And your spinal cord is basically a huge bundle of nerves. And so you can imagine if you have something that pushes against it, which is not supposed to be pushing against them, then all of those nerves are going to fire at the same time. It's going to cause you extreme pain. Yeah. And so I've never had this, thankfully, but whenever I see someone that has it, they look like they look like they want to die, and so it's extremely painful. Okay. And so this can be caused by either traumatic injury, and so if you have kind of a large compressive load on your spine, and if that doesn't fracture your spine, then it could cause one of your discs to pop out. Okay. And it could also be caused by repeated stress. But for the second case, this only really occurs for discs that show signs of degeneration. Okay. And so for the second case, this is something that kind of happens over a long period of time. Okay. So the most common places for disc herniation is going to be the bottom of the cervical vertebrae. And so kind of near the bottom of your neck, right? So remember your cervical vertebrae are the very top of your spine, or at the very bottom of the lumbar vertebrae. So kind of right above your butt. Okay. And the difficult thing about hernias is that they're difficult to detect, if they're about to happen, because typically if you have some kind of pain, the first test that doctors will do is some kind of X-ray, right? And so the X-ray will check to see if you have any fractures, but it can also check to see if your bones are kind of misaligned, in some way. And so the difficult thing about hernias is that, the space in between your vertebrae don't actually change all that much when you have a hernia. And so from an X-ray, it's difficult to diagnose. Okay? And most of the time, hernias are treated what's called conservatively, and so without any kind of major surgery. But if you have a severe case, then that may require some surgery as well. All right. Any questions on hernias? Okay. All right. And the last injury that I want to talk about is whiplash. Okay. And so whiplash, this basically happens whenever your neck undergoes sudden acceleration and deceleration. Okay. And so one common case where this can happen is if you're in an automobile accident. And so this happens a lot when you're rear-ending. And so when you're rear-ended, what tends to happen is that normally, when your neck is going through normal motions, your brain can kind of anticipate what the motions are. And so it can kind of preload your neck muscles to kind of prevent any kind of wild actions from happening. And so what's dangerous about getting rear-ended is that, your brain doesn't expect you to be hit in the back. And so it doesn't have time to really react and make your neck muscles kind of stabilize your head. And so, when you get rear-ended, your head kind of does this kind of really crazy motion. Not because the impact itself was severe, it's just that your brain just didn't really have time to react. And so because of that, because your muscles aren't really there to provide any, to take on any of the load, basically all of the load of this action right here is going to be taken by the spine. And so that's and that's what causes injury. Okay. And whiplash is one case where, you're going to have severe shearing forces. Okay. And so it's a little bit different compared to, the cases we talked about before, where most of the forces are compressive. Whiplash is dangerous because it provides a lot of shearing forces, which, is a whole nother ballgame in terms of, bone stability. Okay. And so if you have whiplash, some of the symptoms include neck pain, muscle pain, or numbness, radiating from the neck, arms, or hands. And oftentimes it comes with headache as well, because, a lot of that pain kind of gets transmitted up to your head. All right, and so I think that's it. So are there any questions on injuries here?
I think whiplash common among like boxers or just combat athletes in general, or would it be different? Like, because I would be assuming that like a strong punch would be coming from the side and not necessarily from like a jab. You're getting like a much power. Can you still get whiplash going like that way?
Yeah, it's a good question. I'm actually not sure. I think I would think that it would be definitely more common among boxers, because it's kind of a similar thing where like, you have kind of a sudden load coming in, and a lot of times, like if the boxer did see it coming and they could react, then, they can kind of brace themselves. But a lot of times, you watch them and it seems really clear that they didn't really expect it coming, and their head kind of just goes like crazy. And so I'd imagine whiplash type injuries would be very common among there too. But I haven't seen the statistics on it, and so I'd have to double check. But I would imagine so that they would be.
Because I always think of it like you said, like the rear end where your head's going like this,
Mhm.
and I didn't know if it was really the same kind of force as if your head is like turning this direction.
Oh yeah, no, it's the same kind of force.
Okay, so you're still getting a lot of shearing action.
Yeah. Yeah. So if your head's kind of twisting to the side, that'd be more kind of like torsional force rather than kind of extension and flexion, but it's all causing shear at the vertebrae. Yeah. All right, and so that's all we got time for today. And so thank you guys for tuning in. And so that closes our unit on statics. And so starting on Wednesday, first thing Wednesday, I'm hoping to have the final project specifications, and so we'll talk about that. And then after that, we'll start talking about dynamics. All right, so thank you everyone for tuning in today. Remember to keep working on homework 5. And so I will see you on Wednesday.
this. You remember how I was talking to you after class the other day about that knee injury that I had heard about?
Yeah.
So that it was like that next day, I was on Instagram and like there's another gnarly clip going viral now. I mean, it's not that bad. Definitely not the worst I've ever seen. But like there's this big movement now with athletes in terms of like knee health and like increasing their vertical. A lot of people like to train their calves.
Mhm.
And then also, I don't know, I think it's the serratus, not that, that's an ab muscle, the tibia muscle right here.
Mhm.
I forget what it's called, but, so there, and then there's also a lot of people who like to do like glute ham raises.
Mhm.
And then the opposite of that, which would be like